Yeah, and then just
Good afternoon, everybody, and welcome to this session of the CIC Rubber Chemistry and Technology Division. My name is Richard Pazer of the National Defence of Canada. Very happy that you can be with us this afternoon, taking some time away from your very busy schedule. Today, we're very excited to have a speaker. He's well known in the rubber industry. He presents a lot at the American Chemical Society Rubber Division conferences, Mr. Paul Tuckner. Paul has a wonderful experience in the area of compressive stress relaxation. So I would say his name is almost synonymous with compressive stress relaxation. Paul is currently the president of the Grace Technology and Development. His current business focus is the development and support of test methods useful for measuring and integrating material properties into design. A primary part of his business is promoting and supporting the use of compressive stress relaxation testing. Prior to starting this business 14 years ago, he had worked at Danyon 3M for 28 years as an R&D application development and materials engineer, specializing in fluoroelastomers and fluoroplastics. He has a Bachelor of Arts degree in chemistry with a master's degree in systems engineering from the University of St. Thomas. He has written and presented numerous SAE, that's Society of Automotive Engineers, and ACS, American Chemical Society Rubber Division papers in the areas of permeation, compressive stress relaxation, and sealing, and he holds 4 patents. So today, Paul is going to give us a general overview of compressive stress relaxation. And I've told him that the talk should be about 35 minutes or so. There is time for questions. If you have questions, please put them in the chat, and I'll go over those questions at the end of his talk. So, Paul, the floor is yours. Please take it away.
Okay, today I'm going to talk about compression stress relaxation. And I'll talk about kind of the introduction and principles of CSR testing, CSR testing configurations, CSR jigs, fixtures and testing, discrete CSR testing and evaluation, comparison of CSR versus compression set testing, CSR standards and specifications, and then finally the conclusion. One of the things that I want to talk about initially is a concept that I've kind of developed is the difference between a standard test value versus a characteristic material response. And I use tensile test as being an example of a standard test value where tensile tests are performed typically at room temperature with a strain rate of 20 inches per minute, with the primary results being specific values, tensile strength at break, elongation at break, and percent modulus. And they're used for comparative purposes. And when you do aging of tensile specimens, the materials are generally aged in the free state to compare them for possible capability and applications, which may or may not be the real strain state in the application. For compression stress relaxation is a measurement of sealing force and its change over time after exposure to fluids at both high and low temperatures. And sealing force is directly related to leakage. Measuring sealing force while compressed and aged is not the same as aging a CSR test specimen in a free state and compressing them. They're 2 different things. And that's what happens when you do tensile testing. What CSR is supposed to do is actually reflect real sealing situations where materials are compressed and they age in the compressed state. There are different approaches to testing, which I often refer to as being comparative, relative, or predictive. And I believe that CSR testing, when done correctly, can be a predictive test. One of the things I like to, situation I'd like to raise with respect to static sealing, and I've worked in this industry for about 30, 40 years, is a static sealing perspective, and that you get a different perspective depending on who you are, whether you're a rubber chemist, a seal design engineer, an application engineer, or a materials engineer. Walk into a room, how would each approach a static sealing application or problem? And they will be different. So I've worked as a rubber chemist and an application engineer and a materials engineer, but never worked as a seal design engineer, but worked with some of those people. So I know each of those people have a different perspective when it comes to sealing. When you look at compression stress relaxation, there's two primary kinds. One is continuous CSR testing and the other is discrete CSR testing. So the simplest version of continuous CSR testing would be testing with a load frame and an environmental chamber, which you can use, or you can use a continuous CSR tester that has separate cells that you can put in a temperature chamber, and I'll talk about that specifically. And then you have discrete CSR jigs where you put a specimen inside a jig and you test them at specific intervals using different techniques to note how that sealing force changes as a function of time. One advantage of discrete jigs is that you can test more specimens under more conditions as compared to the other ones. Now this is a typical load frame setups in my lab. I have an Instron and an MTS machine. And if you wanted to compress a test specimen on a pedestal like that, you could do that and run the test like that. If you had an environmental chamber around those configurations, you could do it at different temperatures also. Here's a case where I've developed two small environmental chambers. One is actually a high temperature chamber where you can take a jig and put it in this chamber. It's an insulated quartz chamber, and then do load deflection curves as it's cooling down, and I'll show that in a second. The other is a controlled temperature chamber that has conditioned air fed in, and then you can check the sealing force on the seal in that configuration. And that's also a configuration you can use to check for leakage, and I'll talk about that in a second. So here's another picture of the high temperature chamber where you would take a jig out of the oven, place it in the quartz chamber, insert a thermocouple into the CSR jig, put the indenter pin in, and just run the CSR test like you would normally at room temperature. But what you do is if you can monitor the temperature as the jig cools, you can do load deflection curves and then determine what the sealing force is and see how it changes as a function of time. And you can see in this graph that the sealing force decreases as the temperature drops. And that's typical of the issue of with respect to differential thermal expansion, which I'll talk about in just a second. This is a case or a picture of the temperature chamber where I did a study and actually evaluated the difference in percent sealing force versus percent compression over a low temperature range. So the material was put in there, it was compressed at room temperature, allowed to sit for 30 minutes, and then it was cooled down at a given rate to low temperature to note the sealing force. And then the internal of that chamber was pressurized with air to note when there was flow. So there was a flow sensor in there. So you could tell whenever there was leakage, the flow would begin to show. So what it shows is that at lower temperatures, not only do you have lower sealing force, but you actually lose sealing force at a higher temperature. So it doesn't seal to as low temperature as it does at the higher compression. The other thing it shows is that the sealing force is lost at the point where the effective sealing force is zero. So you can see that each of these cases show that the sealing force here is lost, or the leakage occurs when sealing force is lost. This is a graph that I put together that I call the viscoelastic response cycle. And what it really does, it kind of shows what happens to sealing force if you're doing continuous readings and the related discrete readings that would come in. So in the first part, if you take a specimen and you compress it at room temperature, it would be a simple compression up to a given point of strain. If you hold it at that point of strain, then you see the relaxation curve of that. So in the relaxation curve over a period of 60 minutes, you would get to this point. So after 60 minutes of relaxation, that value is the initial value used if you're doing discrete CSR testing. Then if you were to heat it up to elevated temperature, you'll see that the sealing force will increase to a point. when you stabilize at a high temperature, and then it'll begin to show relaxation at that point. And then if you cool it back down, you'll come to a point which will have a sealing force lower than your initial drop that you had with the initial relaxation. And this has to do with the high temperature relaxation that occurs just from exposure to the high temperature. And this value is something you can test with discrete jigs by, after you do the initial sealing force check, you can put it in the oven for 1 hour, take it out, allow it to cool, and then check the sealing force again. So whether you do this continuously or do this with discrete jigs, as long as you follow these same positions, you should get the same number. And then if you, at this point, if you take it out of the jig and allow it to sit for like 30 minutes or 60 minutes, the specimen should recover a certain amount to what it was originally. And that's what I would call the initial compression set, or the room temperature compression set value. Then if you take the material and heat it back to elevated temperature for a short period of time, so let's say it's 30 minutes or 60 minutes, and then take it out and cool it back to room temperature, what you should have is that thing should recover to its original shape and thickness, assuming there's no degradation of the material. So this is a characteristic response to the material that shows how you can compare continuous testing to discrete testing and how they compare in an actual application. One of the things that people don't understand or don't talk about is what I call differential thermal expansion and effective percent compression. So if you look at some of these configurations, this is considered a series compression, and this is a thing called statically indeterminate. So if these two are locked in position and you heat this up, what you'll find out is the stiffer material will compress the less stiff material, and you'll get a value. And this is a parallel constrained configuration where you're working with two of them. Now, what happens if you actually do continuous testing, you typically have a series constrained configuration. So the amount of compression that actually occurs here will depend on the length of the compressing surfaces, their stiffness, and their thermal expansion. In most applications for sealing, you really have a parallel configuration, which is what you see in a discrete thing. So you have to understand that if you're doing continuous versus discrete testing, you might not get the same values unless you have matched thermal expansions and distances to compare. Now, so for continuous testing, this would be a standard test piece of equipment. This is the Elasticon, and they have newer ones now that have more cells. So this one has 3 cells. They have ones that have more cells. This is just a heated controlled chamber. They now have ones that can both heat and cool. And one of the advantages of this is that you can follow multiple specimens at over a temperature range up and down, and it gives you really good values. The disadvantage of this is that there's some configuration constraints that I get concerned about on this. And also it's a very expensive unit. I think the bigger unit that can do both heating and cooling with multiples is around $100,000. And it's really good if you're doing short-term type of testing. But if you're doing long-term, you're using the capability, a real high performance capability really isn't necessary for long-term for an expensive material. For discrete jigs, there's several different, and the first one I was familiar with was a Lucas stress relaxometer. And that was like in 1980 when I first saw that. And that used an electrical contact brake configuration. And then later on, I got involved in the Chabray-Wallace, both the tester and the jigs. And now they have the Wallace tester with the Wallace jigs with the new tester. And those are both electrical contact brake. Then there was the Wickham-Ferentz jig, which had its own tester. And then there's the Jones-Odom jig, which Ford was using some time back, and the JMAC jig, which Chrysler was using. And then I developed Grace Technology jigs and fixtures when I was at Dyneon 3M at the time. And that can use both the electrical contact and load deflection. So this is what the Chabray-Wallace looks like. And the jig, I think, is similar to the one they currently sell. The tester that we got was a pneumatic one. They have a new one now that's electromechanical, but the principles are still the same. There's a preloaded spring in this part that you standardize on, and then you compress your specimen. And then when you do the deflection, it separates the electrical contact brake, which defines a load at that point that tells you what the sealing force is. This is a Jones-Odom jig, which was a really good design. what they use is they use a linear bearing indenter. And that was to ensure that the specimens were loaded in parallel faces, actually down the center of the specimen. And but the problem with this is that it used large compression set buttons and the jigs are very large. So by comparison, this is a newer design of the Jones Odom jig, but it's still pretty large. This is the Sharbury-Wallace jig. This is the JMAC jig. And this is the Grace Technology and Development O-ring jig. And this is the ASD jig. So you can see that, you know, as you work from left to right, you get smaller jigs and you can test different kinds of specimens. So one of the unique things about the ASD jig is they use a centering feature which uses wedges and a centering cup, which centers both the shims and the specimen in the jig, which is important. And then I developed an indenter pin, which has a tripod base and a hemispherical head, and it's hardened so that it works really nice to accommodate off perpendicular loading in your test configuration. And nobody had really done that, and it really makes a difference in the quality of your load deflection responses. So this is the load deflect. This is the CSR test configuration that I use in my lab. So on the top, you see the load cell, and below that, you see a contact plate for a deflectometer. So you can have a deflectometer here, and that allows you to measure the actual deflection that's occurring and takes out the deflection that occurs in the load cell, which helps you obtain a higher stiffness ratio, which I'll talk about in a little bit. And then there's a plunger here, which is a small cylindrical thing that's hardened that runs up against the indenter pin that allows you to do the deflection. And then there's a pedestal, which is hardened and locking, just like the plunger is, so you don't have any slack in the system. And then there's centering pins that allow you to slide the jig right up against the centering pin that ensures you're on center. So it makes it easy to do the test, and it's a really nice test configuration. So when you run the load deflection test, what you do is you get a response curve that you see on the right. So the first part is what's known as a system response, and the second part is a sample response. So this is initial part is when you're compressing, you try to compress the top shim. You try to deform the top shim, and this is what happens as the load increases before you exceed the sealing force. Once you exceed the force that the rubber is exerting on that top shim, then what you begin to do is you start compressing that specimen at this point. So this gives you a different slope, and that the inflection region or the inflection point is the sealing force that you've overcome to get these two responses. So one thing you get out of this is if you take the ratio of the system stiffness and the sample stiffness, which are the slopes of the two, you get what's known as a stiffness ratio. So what I say when you do CSR testing is you want to have a stiffness ratio that's greater than 5. And if you have a stiffness ratio that's between 2 and 5, then you need to note that. And depending on how linear your response is and the quality of your inflection region, you may be able to say that, okay, this is good and I still have a valid value. If the stiffness ratio is less than 2, I say that you can't really say with any certainty that those values are correct. And so one of the things that this allows is that if you're doing sample stiffness and you note that over the test period, you can see that the sample stiffness may change. And some materials that age by diffusion limit oxidation will have an increase in sample stiffness over the testing period. Let's say if you're doing nitrile testing aged in air, you'll see that sample stiffness increase. And at some point during the testing, you may find that your stiffness ratio gets too low that you can't see an inflection point. And that can happen in certain cases. So having a good load deflection curve response and knowing what that means is really important in getting good CSR results. One of the things about the ASD CSR jigs is you can take them and put them in baskets. So these are baskets that I've used in doing testing in fluid. So on the left is a pressure vessel. So you can put 18 CSR jigs in that basket and then lower it into the fluid in the vessel. And then when you're put the vessel in the oven or in a heated controller, when you come to the time intervals, you can take them out and you cool the vessel down, you take them out of the vessel, you pull the basket out, and then you let all the fluids drain back into the vessel. And then you can pull the jigs out, wipe them down, put them in front of a fan and cool them and run the CSR test. So it's a real efficient and effective way to do CSR. Another thing you can do is, here's a jig that I designed for oil and gas that actually has a special shim on top that allows you to put a swage lock fitting in there that allows you to do leakage testing. So you can do CSR testing and measure the sealing force, and then at intervals, you can check it for leakage, or you can do both at the same time if you have the right configuration like I showed earlier. The biggest thing about CSR testing is that you can't get any better quality of results than the quality of your load deflection curves. And I've seen some cases where I see the load deflection curves are really bad. They're not linear, they're curvature, they have peaks all over the place or things like that. So you can't trust things like that. And I'll talk about that later about quality of the test system. There's a Dilbert comic that I saw one time that I thought was appropriate and relevant. It said, which option costs the least in the long run? And it says, we don't have any accurate data to determine that. Then use the inaccurate data. I'm not saying our data is mildly flawed. I'm saying it's so inaccurate, it's useless. But it's the best we have yet, but it's all wrong. Go ahead and use that data. Why would I want to use data I know is wrong? I know if you remember the part, I don't know if you remember the part about being the best data we have. So my concern is that make sure that the data you're providing is high quality. And I'll talk a little bit more about issues related to that later. Okay, one thing that you look at when you look at a CSR jig is really a compression set fixture if you want to use it for that. So what happens is that when you compress it in there, your initial specimen has to expand radially in order to keep its same volume. And then when you heat it up to elevated temperature, because it's constrained axially, it also will expand radially. And then when you cool it back down, normally it will contract radially to its equilibrium position. But in some of these cases, when you do long-term testing, such as Baymax, Asian air, oftentimes those test specimens will begin to start bonding to the interface at elevated temperatures, so that when you cool them back down, they can't contract uniformly. So they actually get cupped in from the sides, and then they actually contract axially, which reduces your sealing force. So knowing what's happening in these things is really important. So one thing I developed along with CSR testing is I developed actually 4 different compression set values, which give you some additional information about what's happening in the CSR test. So the original one, the first one I did was I call the shim set. And the shim set is where you remove the specimen from the CSR jig in contact with the shims, and then you measure the thickness of both the shims and the test specimen, and then you subtract the thickness of the shims to determine what the compressed thickness of the specimen is in contact with the shims. Then at that point, you separate the shims from the specimen and note the adhesion that you have, because that's important. And then you let the specimen sit for 30 minutes at room temperature to recover. Then you measure it at that point. And then what you do is you put it back in the oven at the test temperature for 60 minutes. And then you take it out of the oven, let it cool back to room temperature for 30 minutes, and you check it again. And that's what I call the permanent set, which is a standard compression set kind of test. And then what you do is you take a digital caliper and you measure the thickness at the edge of the specimen. And that's what I call the edge set. So for materials that age by non-uniformly by diffusion limited oxidation, you find that the edge set is greater than the permanent set. So it gives you some indication of the uniformity of degradation. So all of these 4 different compression set values are useful to give you some information on what's happening with the specimen in the CSR jig. So what you can do is you can do this at the end of the test, but if you want, you can add additional jigs you can take off test at the different intervals. And when you do that, you can see the progression of all 4 of the different compression set values. And you can do that along with the CSR testing you do, because you'll have more additional values. So you'll see that the shim set is the highest, then the initial set. And then what you'll find is that the edge set is typically higher than what the permanent set is. And then if you take and plot the shim set and the permanent set values against the CSR values, what you can do is you can get a linear regression, and you can see that the shim set values, the intercept point is near 100%. So it shows that when your shim set is 100%, it coincides with 0 sealing force. So being able to have both of these gives you some information on what's happening. And sometimes if the degradation is not uniform, it skews some of these values. Another thing you can do is you can do configuration testing. So this is some work I did about 20 years ago where I evaluated different size specimens and shapes and compared them. So what you can do is you can look at the effect of size, shape, and percent compression on the CSR response. And in this case, when I was doing FKM testing, I showed that specimens with the same shape factor, which is a ratio of diameter to thickness to diameter, they all had the same retained sealing force. And that specimens that had high shape factors, which were large diameter, small thickness, had poorer retention of sealing force. And the ones that were taller with smaller diameter had better. So it gives you some idea of the effect of shape and size on that. Additionally, you can do the effect of percent compression to determine the optimum percent compression. So in this case, it shows the percent retained sealing force, and it shows that at low percent compression, what you get is you get lower sealing force, which makes sense, but you actually lose it faster. And that intermediate region, you have the best retention of sealing force. And at high percent compressions, you have higher sealing force, but you lose it faster. So at some point, you end up having less sealing force than what you would at an intermediate range. So from that, it gives you some idea of how to optimize percent compression. And that depends on material, max temperature, and fluid exposure you're dealing with. So each of those will affect that. The third thing is mode of degradation. So in this case, where I noted previously that if you had specimens that had the same shape factor, but different diameters and heights, you should get the same percent retained sealing force. But in this case, with some orange HNBR specimens, you could see that they degraded from the outside in by turning black, but it's a larger percentage of the small one than it is of the large one. So you'd find that the percent retained sealing force was best for the larger specimen and worse for the smallest one. And if you did this same thing with O-rings, you'd find that O-rings of the same diameter that were thicker would have better retained sealing force than ones that were thinner. If you had a material that aged uniformly, you'd find that the values are pretty much the same. So that's really important that you know the mode of degradation and how it affects percent retained sealing force. In this case, you could see a button that was actually domed in the center. So you could see that the edge set was much higher. When you talk about CSR test standards, there's pretty much three primary standards. So there's ASTM D6147, and then there's ISO 3384, both part 1 and part 2. And then there's a SAE J2979. Of these three, the J2971 is the only one that actually tells you how to determine sealing force. The other ones just say, this is the test, you can use these jigs, and then this is how you report it. So the SAE J2979 specifies a given jig, which is the ASD jig, and also tells you how to perform the test and then do the analysis, which the other ones really don't. And I'm in the process of updating SAE J2979 for some of the things that I think are important since it was originally developed about 10 years ago. And again, I want to reiterate the difference between a standard test value versus a characteristic material response. And I kind of developed a concept a couple of years ago, which I call precision CSR testing. And again, the quality of the CSR results will depend on the quality of your CSR test system and its limitations. So these are some of the questions I discuss. Is your load frame or CSR tester capable? And there's approaches that I use to look at that. And is your test software capable? I use a certain approach both with MTS TestWorks and the Instron Blue Hill 3 that works very nicely. And is your load frame fixtures capable? Are your CSR jigs and test fixtures capable? Is your procedure capable? And are your test engineers knowledgeable? A lot of time test engineers are responsible for the CSR testing, but they don't do the testing. They have technicians that do it, and they may or may not give them the information they need in order to assess the CSR properly. The people that deal with CSR are people that are concerned about long-term performance under high temperature and fluid exposure conditions occur. where failure can result in high cost or loss of life. And it has to do with trying to understand the capability and service life of not just the materials, but the designs they're using. It's primarily used in automotive for GM, Ford, Chrysler, aerospace. I've done work with Wright-Patterson Air Force, UDRI, and the SAEC committee. And then in the oil and gas business, I work with Baker Hughes and Schlumberger and a few other people. Semiconductor, which is a huge thing that I don't think really uses CSR right now, but when they're doing fab situations, if they get a leak in the fab and they ruin a whole chip on that, a big disk, it's very expensive and things like that. And then in cases where there's industrial applications. So the things that I look at for CSR is not just the testing, but testing in a way you can integrate material properties into design, to define capability and service life. So you're looking at the full material response and compression, the characteristic material response, which is the stress strain response, being able to differentiate the viscoelastic response from degradation effects. So usually the first change in sealing force is primarily due to the viscoelastic response. And then the later part is degradation. And in between, you have a little bit of both. And then what I talked about a little bit about the configuration effects, which has to do with design, and that has to do with size, shape, and percent compression. And then understanding the mode of degradation and doing an evaluation for that. And understanding whether when you have a failure, is it a material issue or a design issue, and doing seal optimization. So in conclusion, nobody really cares about materials, designs, or testing until you have a big, expensive, or critical failure or loss of life. Then it becomes an issue. CSR can be considered just another compression set test, but then it can only be used as a value for comparison. When performed with good equipment, knowledgeable operators, and good controls, full or expanded CSR testing provide good information which allows you to optimize a design and predict capability and service life. So thank you for your attention, and I'll take any questions you might have.
Okay, thank you, Paul. This is a nice summary of compressive stress relaxation testing. I was looking in the chat, I didn't see any questions, but to our participants, if you have any questions, please put them in the chat and I will convey them to Paul. I have a couple questions for you, Paul.
Sure.
First one has to do with O-ring testing.
Okay.
So you mentioned that these jigs you're performing static testing.
Yes.
But we know O-rings are really, it's under a dynamic environment, dynamic compression. Is there a way to do dynamic compression testing with your jigs using your O-ring jig?
I'm primarily focusing on static sealing, so they're
Right.
not necessarily dynamic applications. Usually in dynamic applications, one of the issues that comes into that is lubrication and abrasion resistance. If you have moving surfaces, so if you use like a piston seal or things like that, the principles of CSR still apply, but one of the big issues you have in that is the amount of loss of material due to abrasion or just wear over time. And but I've done some work in developing an approach to actually doing radial sealing CSR testing. So I've got a design that I've done that, and that would be a case where you could potentially put something in a dynamic situation and actually test it dynamically, and then have it checked periodically for its contact force in a radial configuration. So most of the applications that I deal with are places where you've got seals in an axially compressed configuration. But you also have situations where you've got static sealing in a radial configuration, and it can be used for that. And like I said, it could also be done dynamically if you want to build a configuration that could measure that, which could be done.
Okay, Paul, thanks. Still no new questions in the chat. I do have another question for you. You mentioned that the best standard for CSR testing is the SAE J2979,
Right.
and you're working to revamp it as well. And then you mentioned the different OEMs, the automotive, aerospace, oil and gas sector, who are using this standard. So are they writing up specifications based on this standard and forcing their suppliers to actually do CSR testing? Yeah, how relevant is it? How widespread is the CSR testing today?
It kind of depends. I mean, what happened is when I originally developed the ASD jig, I did it because I did a comparison of all of the jigs that were available at the time. So I did the Sharberry-Wallace jig, I did the Wickham-Ferentz jig, I did the JMac jig, and also the Jones-Odom jig. And what I found is that, it was either some of the jigs were either very expensive, or the jigs were too large, or they didn't have the centering feature in that. So what I did is I made the ASG jig smaller so that I could fit more jigs in a smaller area, and also developed a centering feature on that because none of the other jigs had centering features, which I realized if you don't have a centering feature, if you put something in a jig and it's not on center, you don't have an axial force you're actually measuring. And if you do low deflection curves, you get offsets in them, which aren't good curves and things like that. So each of the jigs have certain deficiencies. It's like the Sharberry-Wallace or the Wallace jigs. They're fine, but they're really expensive. And there's also an issue with the electrical contact brake, which we found not only in my lab, but work I did at University of Dayton through the Wright-Patterson Air Force Base, that they were having trouble getting good contact brakes and there's other issues with the preloaded spring and how it changes with time and things like that. And they can't really be used in fluids very well and stuff. So the objective was to try to get a reasonable size jig that you could do multiples of that would have good configuration control. And eventually I developed another jig, which was called the HP jig, which was for a high pressure jig, because I was working with Baker Hughes and they use high pressure part pressure vessels, which have a center diameter of 3.5 inches. And they couldn't fit 3 of the ASD jigs inside that pressure vessels. So they said, can you make us a smaller jig that could test the same specimen, but fit 3 of them in? So I made the HP jig. And what I did is I actually not only made the outside diameter of the jig smaller, I made the inside of the jig diameter larger so I could use larger shims. Because the original ASD jig was designed for 25% compression. But if you wanted to do higher compression, you run the risk of having the specimen slide off the shim. So I wanted to have a larger shim. So if I wanted to do higher percent compressions, it would allow that. So that's how that HP jig, but the principles are the same with the same centering cup and indenter pin and same configuration. And then people said, can we do O-ring testing too? So I said, yes, you can do O-ring testing. So I took the original O-ring design I had from 3M and I made the center cavity larger so you could do not just O-ring compression between 2 plates, but you could actually put it in a grooved shim, which is how it's used in the application. So you can use grooved shims. You can put the O-ring in the groove shim, either with internal pressure, external pressure design, and it would be the configuration you'd find in a real design application. So you could do that. So I've accommodated different jig designs for different applications and different people. And but the principles behind the jigs are pretty much still the same.
Okay, thank you. Still no questions. I have one last question for you.
Sure.
You talked about the quality of the testing and the testing results, and I know you put a lot of time and effort into it and a lot of factors. And I know that you recommend that we run at least 3 repeats.
Yep.
Correct? At least 3.
Yeah, there's 3 deflections. So what I do, originally they said to run 3 deflections and take the median value. And I contend that the median value is not the correct value. people use the median value when they do tensile tests.
Right.
But part of that is because you get outliers with a bad break. So it eliminates outliers. But with CSR testing, you're testing an intermediate equilibrium response is what I call it. So what I found is that with good CSR testing, usually what happens when you do 3 deflections, your first deflection is a little bit higher. And that has to do with separation of the adhesion between the top shim and the cap of the CSR jig. And it may have to do with just a little bit of interface movement on the specimen. So on a good CSR test, you'll find that the first value is higher. The second value might be like 1 Newton lower. And then the third value should be close to the second one.
Mhm.
So what I do is I say you should take the third value if it's close to the second one. If it's still not close, you can do multiple deflections beyond that until it stabilizes. And you can always run additional. So sometimes I'll run 6 deflections and I'll see that the third deflection is pretty close to the second. And the ones after that really don't change that much. So then it kind of reinforces the idea that the third deflection is a good value to use. So that's one of the changes I'm recommending in the SAG 2979 as a way to approach it, and trying to suggest a logical reasoning behind why you do that rather than just say, this is what we've always done.
Okay, great. Thank you, Paul. I don't see any further questions. I think you did a great job
Okay.
going over everything, and there's people just don't have any questions for you because you were so thorough and so detailed in your approach. You are definitely an expert in the area of compressive stress relaxation.
I mean, one of the things that these things only cover a part of that. So, I mean, I could spend a half hour talking about the compression set testing. I could talk about low deflection curves and offsets and things like that. So you could take each one of those sections into a lot more detail. But I just wanted to show it so people have some idea the differences and why you might choose one or the other and what they would really be useful for.
Okay, thanks, Paul.
Okay.
I think we're going to conclude our the presentation for today, the virtual
Okay.
seminar. Thanks again for your participation. Very interesting. And if anybody has any questions for Paul, he's got his contact information here on his last slide, his email and his phone number. And to conclude, I'm just going to mention that we do have a speaker lined up for in September. And I still have to finalize getting him signed up, and I will put that information on the website. And before I forget, Paul's presentation today has been recorded, and it will be put on the website probably sometime next week. So thanks again for attending today. Enjoy your Thursday afternoon, and enjoy your summer, and we'll see you in September.
Okay. Thank you, Richard.
Yep. Bye, everybody.